you are.
Thank you.
Yeah.
Well, that was awkward. Not as awkward as going to the dentist. They always yell at you for not flossing and haven't yet figured out that we can't respond with our mouths wide open. So it's pretty ironic that for my chemistry PhD, I researched dental materials. Things like caps, crowns, cavity fillings, and dentures that make the reconstruction of teeth possible. So let's take a sec and really sink our teeth into the history behind dental restorative materials. Dental amalgam was first introduced in the mid-1800s and is a liquid mercury and metal alloy mixture. So if any of you have a silver cavity filling, that's dental amalgam. But despite the fact that this material is low cost, superior in strength, and prevents bacteria from reproducing, there's a bit of a controversy about having heavy metals in our mouths. So with that, the dental industry turned to polymers. Polymers are large molecules made up of repeating units. So if you think of a polymer as a Lego structure, it's made up of repeating Lego pieces that we call monomers. There are plenty of everyday examples of polymers, including plastics, synthetic fibers, and if any of you have a white cavity filling, that's also a polymer. But this dental polymer has some problems. This material starts out as a liquid, and as it hardens, it shrinks. So if you're trying to fill a cavity with a material that shrinks, you lose adhesion to the tooth. This material also tends to break down in the presence of water and acid, and our mouths are quite wet and acidic. What this means is we do not yet have a permanent solution for dental restorations. This is where my research comes into play. Our lab said, hey, let's use a different polymer system that is more stable in liquid environments and does not shrink as it hardens. In my research, I take a little look at the big picture and address two main drawbacks to our system. The monomers that we decided to use smell a little bit, which isn't great for mouth applications, and the monomers can harden prematurely, which limits its use in a dental clinic. In my research, I make structural alterations to the monomer and see how that affects the polymer. I look at things like, how much does the monomer smell? How hard is the polymer afterwards? And I compare all of these values. In this way, I've optimized which monomers don't smell, which monomers don't harden prematurely, and I'll use this information to make an even better dental material. Because the Center for Disease Control reported that 91% of American adults have dental cavities. This fact still hasn't convinced me to floss more, but I think it would be so cool to see the material I'm working to develop end up in somebody's tooth. And maybe then I'll be a fan of the dentist. Thank you.